Hi there. This video is going to walk through a brief example for application of the particle in a box model to a conjugated hydrocarbon. So in lab, you're going to do an exercise that has you assess the appropriateness of the particle in a box model that we've been talking about in class for predicting the UV-vis absorption spectra of conjugated dyes. So to do that, you're going to record the UV-vis spectra of a variety of different conjugated dyes of different lengths, and you're going to compare different families, and you will use your data to assess whether that particle in a box model is actually a good model for describing the pi electrons in a conjugated system. Some assumptions that you're going to make in your analysis in using the particle in a box model for this application are going to be that the pi electrons in your molecule are delocalized over the entire length of that conjugation. So however long your string of double bonds is, your conjugation, that's essentially going to make up your box for your model. Another assumption that you'll make is that you're going to assume that your molecule is rod-like or linear. Okay, so again, we're looking at the idea of matching up to the particle in a box model, which is also known as a particle on a line. So that electron, remember in our model, is moving in a linear straight path. So you'll have to think about whether or not your molecule is a good approximation to a rod-like or linear molecule, and that might give you some information about how appropriate the particle in a box model is for your particular molecule, but I will leave that for you to assess. The third assumption that you're going to make here in applying the particle in a box model is that we also want to assume that the potential energy along that conjugation is zero. So remember, inside of our box, the potential energy is zero in our particle in a box model. And then we're also going to assume that the endpoints are infinite potential, right? So we're keeping our particle inside that box. Again, this is something where you might want to think about how applicable is this assumption to your specific molecule that you're looking at. Okay, sometimes it might be a fairly good approximation, sometimes it's not. So these are some things to think about as you're kind of drawing your conclusions when you look at your data about how good this particle in a box model is for describing the particular systems that you're looking at. All right, so we're just going to do a simple example on how to apply the particle in a box model to a conjugated system. Your laboratory instructions will have a little bit of a different approach that you're going to use, mostly in how you account for the length of your conjugation. Okay, so make sure you follow those directions for your lab analysis. But this is just going to be a basic example of how we can apply the particle in a box model to predicting the absorption spectra of a conjugated molecule. Okay, so our simple example is butadiene, so a nice simple 4-carbon molecule. Okay, we can see that our conjugation chain goes from this carbon here all the way over to this carbon here. So these are essentially going to be our endpoints. Okay, so carbon to carbon, and this is our length of conjugation. The first thing we want to do is to figure out how many pi electrons we have in our conjugated system, and that's the number of electrons that we're going to concern ourselves with. So we only care about the pi electrons because those are the only ones that get delocalized and can travel. Okay, so in this molecule, we've got 2 double bonds. Okay, so that means that we have a total of 4 pi electrons that we want to consider. Be specific there. 4 pi electrons. Okay, so the next thing we want to do is to try to approximate how long our box is. So we want to have an idea of what is the length of conjugation that these 4 pi electrons are going to be able to travel. Okay, so in order to do that, we're just going to take into account the bond lengths, approximate bond lengths of our carbon-carbon double bond and our carbon-carbon single bond, and we're going to just add those together to come up with an approximation for our box length. Okay, so you can look up these average bond lengths in any textbook or online resource. Okay, so you should end up with values that are approximately on the order of what I've written down here. So a typical carbon-carbon single bond is going to be about 1.54 angstroms. Carbon-carbon double bond a little bit shorter, as predicted at 1.35 angstroms, and a carbon atom radius of about 0.77 angstroms. Okay, if you are extra adventurous, you could make this molecule in Spartan and get some calculations going to come up with values for these. Okay, either way, look them up, do a Spartan calculation, whatever you want to do to get some values, reasonable values to use. Okay, so let's add them up. Let's add up all of these components of our conjugated chain for our example here. So we have, looks like we've got 2 carbon-carbon double bonds plus 1 carbon-carbon single bond. And then at our endpoints, we're just going to count for 2 carbon atom radii to cap off our conjugation length. Okay, so this would give us an approximate length of our conjugation chain, so we can plug in the values that we have corresponding to those different types of bonds. So that's 1.35 angstroms. We have our 1.54, and then 2 of our atomic radii. Again, just remember we're just accounting for the other side of that carbon atom, right? That's on here, in here, that's not part of that double bond. Okay, so if we add those values up, you should get something on the order of 5.78 angstroms. Okay, now don't panic if your values are a little bit different, if you used a different resource to look them up. Okay, we're just going for a reasonable approximation for a conjugation chain. Okay, there's going to be a variety of ways that you could approach this, some better than others. Okay, we're just doing a simple example here. All right, so the whole idea here is that we're going to be able to use this particle in a box model to describe the electronic spectroscopy for our butadiene molecule, or UV-Vis spectrum. Okay, so that means that we want to have some information about how these pi electrons are going to essentially get excited when we shine light on them, right? So we're doing spectroscopy, interaction of light and matter. So what happens to these electrons when we put in some light and excite them? Okay, well, they're going to jump to different energy levels. Okay, so we're going to start by drawing some energy levels. Okay, so we'll just start drawing our lowest energy levels here for a particle in a box. Okay, so n equals 1, n equals 2, n equals 3. Okay, and so you can go up higher in energy levels if you need to, but for this example, we're just going to start filling our energy levels with our pi electrons according to our Pauli exclusion principle. Okay, so that means 2 electrons per orbital / energy level. Okay, so put in our electrons. So we've got 1, 2, next 2 go up here, 3, 4. Okay, so there's our 4 pi electrons occupying our lowest energy orbitals, our lowest energy energy levels for butadiene. Okay, so now we're going to ask ourselves, what's going to happen when we excite an electron here? So we're just going to look at one electron transition here. That's going to be our most significant contribution to the UV vis spectrum. Okay, so we're just going to go one energy level up. Let me change my color here. Okay, so we're going to take one electron and we're going to excite it by shining some light in there. Okay, so we say that is a little arrow of light, H nu. It's our photon. Okay, and when we shine light on our molecule, one of our electrons will get excited to the next energy level. Okay, and we're going to do a little calculation to see what wavelength is going to be associated with that transition between our n equals 2 and n equals 3 energy levels. All right, so we already know something about the energy levels of a particle in a box. Okay, so we know that E equals h squared n squared over 8 ma squared. Okay, so hopefully that looks familiar from what we've been working on for our particle in a box model already in class. Okay, that is the expression for the energy levels of a particle in a box. For spectroscopy, remember, we're interested in delta E's. We want to know what the change in energy is for this transition. Okay, so we're changing our values of n here. Okay, so we're going to calculate a delta E for this transition. Okay, so here we're just going to plug in for our different values of n that we're moving between. Okay, so we've got our constants out here still, and then we'll just plug in for our transitions in n. So we're going to do E final minus E initial, so we get 3 squared minus 2 squared. Okay, and then that value, remember, delta E equals h nu, or hc over lambda. Okay, so if you want to calculate the frequency or wavelength associated with that transition, those are the relationships that you want to use. Okay, so these are the equations for spectroscopy, calculating frequencies and wavelengths that you want to really have handy in your mind. Okay, so all we have to do at this point is plug in the numbers for constants. So we already know Planck's constant, right? 6.626 times 10 to the minus 34 joules seconds. Our mass here is going to be the mass of an electron. Okay, so you can look that up in any resource that you have handy. And then A is going to be the value from our calculation that we just did up above. Okay, obviously you want to watch your units when you work with all these numbers, so make sure that you've got your masses and lengths and everything that are going in there for your units. Probably want to put an alternative unit in for the joule in your Planck's constant to make sure everything matches up. Okay, so I'm going to let you take a minute and finish up that calculation to come up with your overall delta E value that we get out here, and we'll meet back in a second and see if you match up. All right, hopefully you took a minute to do that calculation for yourself. So let's see what we end up with. I got a value of 9.02 times 10 to the minus 19 joules. Okay, when I plug all of these values in there. Okay, so when I see this number come out for a calculation relating to UV vis or electronic spectroscopy, electronic transitions, I like this number because I recognize that 10 to the minus 19 joules is on the order of a typical electronic transition energy. Okay, as you start to become familiar with your different types of spectroscopy and your different regions of your electromagnetic spectrum, you'll start to become familiar with the ballpark energies of these different regions. Okay, but for electronic spectroscopy, for UV vis, okay, for visible kind of wavelengths, 10 to the minus 19, 10 to the minus 18, okay, are going to be typical energies. So when I see that number, that's not a red flag for me. I'm like, okay, that looks like a reasonable number. Okay, remember, we always want to get into the habit of asking ourselves, does the answer I get make sense? Okay, it's really helpful if you have an intuition about what your value, what an appropriate value should be for your calculation. It really helps you to discover when you've maybe made a mistake somewhere. Okay, so the next step in our calculation here is going to be to see if we can get a wavelength. Okay, remember when we're talking about UV vis spectroscopy, we're usually thinking in terms of wavelengths, not joules, okay, or energies. So why don't you take another minute and see if you can convert this value of 9.02 times 10 to the minus 19 joules into a wavelength in units of nanometers. Okay, so remember when we record on our UV vis spectrometers, our x-axis is usually nanometers. Okay, so let's see if we can get a value in nanometers. Okay, so hopefully you did that calculation for yourself. You should have obtained a value of about 217 nanometers, or close to that. Okay, so that is going to be, again, our lambda. Okay, so that is our, essentially our theoretical value that we have just calculated using our particle in a box model. Okay. Last thing we want to do is to compare that to an experimental value and see how well our model did. Okay, so remember, we haven't done any experiments yet, right? So all of this is just using our particle in a box model to see if we can predict what we would expect. This is essentially going to give you where your lambda max is. So that's going to tell you where your peak in your UV vis spectrum should be located. Okay, we're not getting any information from this model about the width of our peaks or anything like that. That there's a lot of other stuff that goes into affecting the shape of your spectrum. Okay, so we're not quite there yet, but we can use this model to predict our lambda max. So next thing you would do would be to look up a literature value for the lambda max of butadiene for a UV vis spectrum. And it turns out that that is 220 nanometers. Okay, so if we look at the difference here, so one thing you can kind of take a look at when you're in the laboratory using the UV vis spectrometers is see how significant you think 3 nanometers. So we have a difference of 3 nanometers here. Okay, for a UV vis spectrum, that is really, really good. Okay, the uncertainty in your ability to be able to distinguish 3 nanometers, okay, those spectrometers are not going to be that good. That 3 nanometers is going to be a large difference. Okay, so I feel really good about this calculation. Okay, I feel really good that the particle in a box model actually does quite a good job of modeling butadiene. Okay, and that's not surprising, right? Because let's think about our assumptions. We've got pretty short molecule here. I think it's not a stretch to say that that could be considered a rod-like or a linear molecule. Okay, obviously the longer we get, that assumption might not hold, right? Our molecules get pretty flexible and floppy when we get those really long chains. Okay, so just some things to think about when you're comparing with some different types of molecules. Okay, but for butadiene, a nice simple molecule really fits our assumptions pretty well, and it ends up giving actually a really good approximation for that UV vis spectrum. Okay, and Again, 3 nanometers, really good for UV vis. A difference of 3 wave numbers in an FTIR, way different. Okay, that would actually be a pretty significant uncertainty for something like an FTIR spectrum. Okay, so you really want to kind of take into account the technique you're using, the instrumentation you're using. They're all going to have different sensitivities. Okay, so you want to keep that in mind when you start trying to label a model as quote unquote good or bad, right? So here, really good for UV vis. All right, that's it for my example. I hope that was helpful in showing you how we can apply the particle in a box model to predicting the UV vis spectra of some simple molecules. Thanks.